In this section we took our first steps with Copilot by opening a simple solution and trying a few things. We learned that there are different ways of interacting with it. Directly in the code editor window, via the inline Ask Copilot window, or via Copilot chat. We learned that we can manipulate the outcome by having files open in our IDE, and that there are built-in commands like explain to ask Copilot specific things. And that gave us an idea of what's possible. Each of these techniques will be expanded upon during the course. Then we learned about the theory behind large language models. A large language model is a type of deep learning AI, which in turn is a subset of machine learning. Large refers to both the scale of the model as to the amount of data that has to be fed into it. In a simplified way, training it works by inputting data, which is then tokenized. And that means breaking down the input in smaller units. Links between tokens are formed through self-attention, taking many potential parameters into account. The tokens are stacked on top of each other, creating multiple dimension layers of those token connections. The sheer size is stunning. In GPT-3, which is already outdated at this very moment, there are 175 billion different parameters taken into account, and there are 96 layers of connections between tokens stacked on top of each other. In GPT-4 and whatever comes next, it's multitudes of that. Once you have such a network of links, you can get outcomes from it. Whenever you send the prompt is tokenized, and then using its neural network with the pre-trained data and links and connections between tokens, the large language model tries to predict the next token by following those connections across all those layers, given the previous token and the input. And with that, it's time for the next section. This section is all about prompts and prompt engineering. You will learn what these are, how all of it works beneath the covers when using Copilot, and probably the most important, you will learn a set of techniques and best practices regarding prompt engineering to get better results from Copilot. Let's dive in. Let's talk about prompts and prompt engineering. From our point of view, a developer's point of view, a prompt can be seen as the sentences in natural language combined with one or more lines of code that we send to GitHub Copilot in order to get a suggestion from Copilot. Prompt engineering then is writing those prompts in a certain way to make Copilot generate better or more specific suggestions that are more useful to you. Important to know is that a prompt is thus not just what we as developers ask or write ourselves. The prompt also consists of relevant context, like comments in the IDE, code that's opened in tabs, stuff like that. Things that are useful for Copilot to improve the suggestions and that are included without necessarily needing to type all of it. So that's the prompt. We already saw a few ways to manipulate and improve it in the previous section. For example, by opening the ordered and order lines classes in our IDE. That was already a form of prompt engineering we did there. Alright, so how are prompts for GitHub Copilot generated then? It starts with a series of algorithms that run locally in your IDE and that select relevant code snippets or code from your current open file and other sources. What is considered are 1. The data from your code editor, and that's not only code, that's also the comments in that code editor, neighboring tabs, and a vector database. I'll immediately elaborate on these 3. That does mean that prompts are constantly being generated in the background. Open an additional tab, and a new prompt is probably going to be generated. Write a new piece of code or comment, and a new prompt is likely to be generated as well. It's the prompt library that takes all these potential sources of information. It then prioritizes them and eventually creates the prompt that is sent to the local contextual filter model. So, from the prompt library, which runs locally on your machine, a prompt is generated and that is then sent to that local contextual filter model. This part is important to understand. Prompt engineering is not just about what we do, not just about how we ask questions to Copilot. There's a lot of engineering and continuous improvement that goes into that prompt library, which is a piece of code GitHub Copilot installed locally on your machine. Copilot's engineers are constantly figuring out how to improve the prompts that library generates. That's not to say that what we write can't have a huge impact. We will see later on in this section that there is a lot that we can do regarding prompt engineering. It's just that it's not just us. A lot actually goes on behind the scenes. Anyway, so that prompt is sent to that local contextual filter model, and it's that model that decides if the prompt should be sent to the cloud where the large language model lives. How it does that depends on the prompt and the current session context. If the session is completely new, you may not have enough session context to get good results yet. And the contextual filter model may then decide not to send the prompt, as it's probably not going to result in a good completion anyway. If you've been chatting with Copilot for a while in the same thread, there is a lot of context, and maybe even some previously accepted code suggestions that are likely to result in a good completion, thus making the prompt a good candidate to send. Once the prompt is sent, the rest happens in the cloud, save for the last step. Copilot's GPT, so generative pre-trained transformer as we learned before, is way too extensive and heavy to run locally. So it takes the prompt and it tries to come up with suggestions with completions. Those are then eventually sent back to the IDE. That's the high-level view. I am not just making this up, by the way. This was inspired by a diagram by Alice Lee, a machine learning researcher over at GitHub. Now let's dive into the separate pieces, as the developers behind GitHub Copilot are constantly working on improving the eventual completions we get back. To understand that, we need to talk about the three types of input I previously mentioned, and something they call the fill in the middle or FIM paradigm. The first type of input is our input, the code open in our code editor, combined with the natural language we wrote in the editor as comments or otherwise inputted. We saw quite a few examples of that in the previous section. The second type of input are the open tabs, or rather the neighboring tabs. The idea here is that more context can be given like that because the tabs you have open tend to be the tabs relative to the feature you are working on. Not every single tab is included. If I'm not mistaken, only parts of the 20 most recently opened ones or neighboring ones are taken into account, but take this number with a grain of salt. This is something that is constantly being tweaked. This does mean that we can manipulate the prompt by thinking about the tabs we open. The third type of input is that vector database. That's a bit of a tricky one to explain, but in essence it's again about context and helping Copilot understand your codebase. In this database, your prompts are stored as vectors. You can look at a vector like an encoding of your prompt, so code, comments, anything inputted that led to a coding suggestion. When a new prompt is generated, Copilot compares that to existing vectors generated from prompts that were previously stored in that vector database. If it finds a similar prompt, it can use that as additional context. If it turns out the prompt led to a successful code completion, it helps Copilot get better at predicting what you need. So, in essence, you can look at the vector database as a knowledge database for Copilot, allowing it to learn from previous prompts. Alright, so those are the three types of input that lead to a prompt. That leaves me to explain the last part of the puzzle, the fill in the middle paradigm. Obviously, code is a type of input for a prompt. But it's not just the code before where your cursor in the IDE is located that is taken into account. The code after the cursor is fed into the algorithm as well. That is called the fill in the middle or FIM paradigm. The GPT isn't just trying to come up with what's next. It's trying to come up with what code should come in between. So, a prompt in GitHub Copilot actually consists of a prompt prefix and a prompt suffix, and it's fed like that into the GPT. Feeding it like that into the GPT means more context is given, which results in better code completions. So, when I previously mentioned that the GPT took the prompt and returned a completion, that wasn't the whole story. It actually takes the prompt prefix and suffix and it tries to fill in the gap. And those results are the potential code completions. And with that, you should have a good understanding of prompts and prompt engineering. So as you know by now, we can't control everything. But we do have quite a bit of control over how prompts and thus outcomes, potential code completions, are generated. Let's open our IDE and experiment a bit. Time for some best practices regarding prompt engineering.